Hello, class. So this next lesson is on section 2.6 on a numerical method. Or I should say numerical methods. I have two inside of this one. And this uses the idea of the tangent line. The first order initial value problem y prime is equal to f of x and y with y of x sub 0 is equal to y sub 0. This uses tangent lines to form a linearization. Y is equal to L of x. We have a direction field and a linear element based upon that. But the reason for why this is important to make note is this is useful for when we want to use a numerical method. But the first one here that we have, which is called Euler's method. This is the linearization of y of x at the point x is equal to x sub 0 is L of x is equal to y sub 0 plus f of x sub 0 comma y sub 0 times x minus x sub 0. But the way to actually use this is to take this formula I have here in the bottom, y sub n plus 1 is equal to y sub n plus h times f of x sub n comma y sub n, where x sub n is x sub 0 plus n times h, n being number 0, 1, 2, 3, so on and so forth. Basically, the idea of it is to get to whatever it is we're trying to approximate, however long that takes. And the picture I have here on the bottom shows a solution curve in light blue. And it shows this linearization based upon Euler's formula, based upon, again, that initial point, which would give us this pink point that's right here. But as this picture here is trying to suggest, it creates an error. Since now we have a point that is nowhere near the point it's supposed to be. And this keeps happening every single time that we try to go through this, right? Where we would have, our line based upon this, where this function value could be like right here, but the point is actually down over here, that type of thing. So it goes above and below that line, which means though it's not particularly too accurate based upon that. But despite that fact, it still could be used, excuse me, could still be used for us to approximate these net values. So example number 1, I want to consider the initial value problem. Y prime is equal to 0.2 times x times y. With y of 2 is equal to 1.5. We want to use Euler's method to obtain an approximation of y of 2.5 using h is equal to 0.1. So make note of this, right? Between 2 to 2.5, we need to have a total of 5 steps for us to actually get through that, right? So it's going to take a couple of attempts of this. I'm not going to bore you with me going through every single calculation out, but we'll do a few so you can see what's actually going on for this. So let's jump right in. Y sub 1. For the formula from the last slide, this would be y sub 0 plus h times 0.2 times x sub 0 times y sub 0. So in our case, 1.5 plus h, which was 0.1 times 0.2 times, for the value of x sub 0 for this will be a value of 2 times y sub 0, which is 1.5. Doing this calculation out should give you a value of 1.56. Y sub 2 now takes the value from y sub 1, which is 1.56, plus h, 1.1, times 0.2 times. So now the value for x now, we increase the 2 by h to be 2.1, times the value that we just got for y sub 1, which is 1.56. So doing that out gives us 1.62552. Y sub 3 takes what we just got from y sub 2 and adds to it 0.1 times 0.2 times, now 2.2 times y sub 2. Doing that gives us, bear with me as I write this. Doing that is going to give us 1.69704288. For y sub 4, that'll be y sub 3 plus 0.1 times 0.2 times 2.3 now times y sub 3. That one is going to be 1.775106852. Y sub 5 will be y sub 4 plus 0.1 times 0.2 times 2.4 now times y sub 4. That one's going to make 1.86031198. And this last one will be y sub 6, which would be y sub 5 plus 0.1 times 0.2 times 2.5. Once we get to what this actual value here is, we could stop once we do the calculation for that particular value. So we still need to calculate it, but this would be our last one. And this would then be times y sub 5. So that gives us an approximation of 1.95332758. And just so you could know what happened here, if we got the actual value for this, the actual value is approximately 1.5 divided by e to the 0.4 times e to the 0.1 times 2.5 squared. And that gives us an actual value of about 1.8785, which, as you can see, the approximation is above the actual value. So not exactly entirely too accurate. Now, with that being said, we could go through the process of calculating errors if we wanted to. Absolute error is the absolute value of the actual value minus the approximation. Relative error is the absolute error divided by the absolute value of the actual value. And the percent relative error is the absolute error divided by the absolute value of the actual times 100, depending on what is actually asked for. So Euler's method was one particular type. I present here a second type, which is a little bit more time consuming. You can probably tell by just looking at this to determine why I call it more time consuming. But this is the fourth-order Runge-Kutta method. And this one tries to go about it in the same way as Euler's method, only the difference here now is it tries to compensate for these by, as you can see, doing a whole bunch of function values to try to iterate the way it's going to the next particular value instead of making it be, just the particular line that we had for that and doing another mishmash of calculations to try to decrease that error as much as possible. There's still some error, mind you, but it's not as high. There's also a secondary reason why using something like this is better than Euler's method, and that's because the computational aspect involved in this is actually faster for the computer to do than Euler's method. But y sub n plus 1 would be equal to y sub n plus h divided by 6 times k sub 1 plus 2 times k sub 2 plus 2 times k sub 3 plus k sub 4. And k sub 1 is just the function evaluation at x sub n and y sub n. K sub 2 is the function evaluation of x sub n plus a half times h, and y sub n plus a half times h times k sub 1. K sub 3 is the function evaluation of x sub n plus a half times h, and y sub n plus a half times h times k sub 2. And k sub 4 is f of x sub n plus h and y sub n plus h times k sub 3. So as you can imagine, a whole bunch of calculations involving that, which can unfortunately get time consuming for these, just due to the way that they would be written out for that. But besides the point currently. For example number 2, I want to use that same function from example 1 and the same trying to find approximating 2.5, but now h being 0.25. That way we just have 2 iterations of this to do, but it could still show you how to actually do this. So for this first iteration, we need those 4 function values of k sub 1 through k sub 4. K sub 1 in our case will be 0.2 times 2 times 1.5. Due to the fact it uses the previous known values, which in this case would be the initial values. And that is going to give us 0.6. K sub 2 now will be 0.2 times 2.125 times, so this will be that 1.5 plus h, which is 0.25, divided by 2 times 0.6, which, actually I should probably write that out, 1/2 times 0.25 times 0.6. Just to point out where this came from 2 plus 1/2 of 0.25. Just to make note where these are coming from. This makes 0.669375. K sub 3 would be 0.2 times 2.125 again, times, this would be I forgot to add one more thing on the top here. I probably should put in here before I continue writing. This was 1.5 plus this 1/2 times 0.25 times 0.6. This next one here would be 1.5 plus 1/2 times 0.25 again. But now this would be multiplied by k sub 2, so 0.669375. And doing that is going to give k sub 3 0.673060. Sure, a bad spot to write this one. Put it underneath here. 0.673060546 and k sub 4 would be this would be 0.2 times 2. 0.2, this will be now times 0.2 times, based upon our formula now, this would be just up to h without dividing in half. So the 2 previous ones did that by 1/2. This would be 2.25 now because of that. Times, this would be 1.5. And again, this one is plus h times k sub 3. So in our case, plus 0.25 times 0.6693. Excuse me, I'm copying the wrong number. It's going to be 0.25 times k sub 3, which is 0.673060546 and that makes 0.750 750 7193 115. And then all of this then gets put together into what this actual step is, which is y sub 1. This is 1.5 plus 0.25, which is h, divided by 6 times. I'm not going to write each number out, but this would be k sub 1 plus k sub 2 plus, I made a mistake. K sub 1 plus 2 times k sub 2 plus 2 times k sub 3 plus k sub 4. So as you can imagine, a kind of long-winded answer, unfortunately. But popping this in would give us an approximation of 1.6681496. Now, the second iteration of this, I'm not going to bore you with me doing out every single entire long calculation, but you could simply check them on your own to make sure that these are accurate. But this one takes y sub 1, which is 1.6681496 plus 0.25 over 6 times all those values for k for this new one now. And I'll just write these ones out. K sub 1 is 0.75, 0.66732 plus 2 times k sub 2, 0.83696 39721 plus 2 times 0.76219 47358 plus k sub 4, which is 0.845 274342. And doing this out gives us 1.840238993. Now, mind you, I only did one here. That's such a big step size, so we didn't have to do too much math out for it. But you would use a smaller value of h to get a better approximation. So let me know if you have any questions or concerns. Thank you.